Hi, I'm Mark Feldman, Senior Staff Engineer with Qualcomm Technologies. Today, I'm going to talk to you about choosing the rendering resolution for your game. When it comes to your game's performance, rendering resolution should be a top consideration. However, there's obviously a trade-off between choices. If you choose too low of a resolution, your game will run smoothly, but it'll look blurred and pixelated. If you pick a rendering resolution that's too high, your game's going to run at a very low frame rate, but the detail and quality will be amazing. Now let's take a look at a major industry trend affecting your rendering resolution consideration. Most device manufacturers are shipping devices with ever-increasing screen resolutions. What used to be a screen size of 800 by 480 in 2010 has now crept up to a quite large 2560 by 1600 screen in 2014. And there's no doubt that even larger screens with 4K resolutions, which is 3840 by 2160, will soon be commonplace, especially with users playing your game. Unfortunately, many games we've analyzed over the years use the screen resolution as the same resolution to render to. This is likely the default behavior in many game engines, or perhaps developers start writing their game this way because it's an easy thing to do and then forget about it. Another possibility is that devices used for development and game testing may not be current, and that unanticipated larger size hardware will become available and popular after a game is published. Now, rendering to more pixels will proportionally increase the required workload. This is because most modern 3D game engines rely heavily on pixel or fragment workloads to achieve realistic effects. In this graph, notice that the pixel rendering workload factor, shown on the right side, drastically increases as the rendering resolution increases. Thus, rendering at a resolution lower than the native display resolution can reduce fragment processing by over 9 times in this example. The factor is even larger when you account for your games with high overdraw. So consider rendering at the lowest resolution, which still yields acceptable quality and performance for your game. 1280 by 720 is an ideal resolution for targeting lower-end smartphones and even many high-end phones depending on the content. Keep in mind, it's okay to allow your resolution to scale up for higher-end smartphones, but cap the upper limit. Rendering at resolutions greater than 1920 by 1080 produce rapidly diminishing returns for games, even on high-end smartphones, at a significantly higher performance cost. Now I'd like to cover fill rate bound, which is a term used to indicate that there's a performance bottleneck related to the sheer number of screen pixels that your game needs to render. It is possible that your game is not fill rate bound, and that's something you can easily check by running your game on a device with a larger screen, and then on a small screen, and seeing if performance changes. You can also do this easily with the Adreno profiler, which is available on our Qualcomm Developer Network site. If your game is fill rate bound, then before addressing on how to handle the increased resolution, you can potentially address the problem by looking at any overly complex shaders your game might be using, and also to minimize the overdraw in the scene. Overdraw is a term we use to describe how many times each pixel is rendered to. Let's go over the solutions to fill rate bound games that you should look at regardless if the rendering resolution can or can't be changed. Now, a Z prepass where the scene is rendered twice, once to render just the depth buffer and a second time to render the color buffer with expensive shaders, is usually not a win on mobile hardware due to the overhead of the increased draw call count of doing both renderings. Early Z rejection, which is an integral feature in our tile-based rendering architecture, is highly efficient and usually done automatically. Now, there are a few cases where early Z rejection is disabled, such as when your fragment shaders write depth, but check our Adreno developer guide on the Qualcomm Developer Network for more details. You could also try profiling your game and figuring out which shaders are being used for the most number of fragments or for the most amount of time. Finding these shaders first will give you a starting point for optimization. Lastly, pay close attention to the rendering order of the scene and try to render in a front-to-back order. The skybox or background element should be rendered last. In the Adreno GPU, there's a display engine that can quickly and efficiently scale buffers, accounting for aspect ratios. This hardware scaler is an efficient way to scale up a smaller sized buffer. So because it's fast, because it renders the workload on the CPU, and because you'll be rendering to a smaller buffer, the GPU will run more efficiently. Depending on how your app is written, there are two basic approaches to invoking the hardware scaler with an Android app. In Java code, when you create the GL surface view, just set the rendering resolution with the set fixed size method. In native C++ code, use the native activity class function, aNativeWindow setBuffer geometry, and pass in the aNativeWindow and the resolution and format. 0 should work. Notice that we picked a 720p, a 1280-720 size in this example, but you can find a size that makes sense for the quality you want in your game. 1080p, which is 1920-1080, is also a popular frame size to do your rendering at. A nice side benefit of doing a fixed size render size in your game is that all things equal, it will basically have the same rendering performance regardless of what the screen size the device might have. Now the HUD, or heads-up display, consists mostly of static 2D elements like player information, time remaining, scores, or even a bitmap. These elements are usually rendered last in the frame on top of the 3D rendering. From an artistic standpoint, these elements should be very crisp and rendered pixel for pixel at the screen resolution. Now, rather than use the hardware scaling techniques we just described, you'll need to do the scaling by rendering the 3D elements to an off-screen texture, which is smaller than the screen size, and then use that texture in rendering a full-screen quad, essentially doing the scaling with the GPU. Finally, the crisp 2D HUD elements are rendered on top. Similarly, when rendering your primary 3D screen, you may also need to render other parts of your scene to lower resolution off-screen render textures. For example, many screen space effects like post-processing are done more efficiently by first rendering the 3D scene into an FBO at a lower resolution and applying the post-processing effect when scaling with the full-screen quad shaders. Also, reflection-refraction effects in the scene can be rendered at a lower quality scene texture. Lastly, lower important elements in your game, like non-essential background elements, can be rendered into lower resolution textures. You'll find that many of these techniques can still produce excellent results when executed on buffers that are half size or smaller than the main frame resolution. The key is to be aware of all rendering resolutions used, not just the final main frame size. A great article on effectively using the hardware scaler can be found archived on this Android developer blog site. Thank you for watching. Visit the Qualcomm Developer Network to learn more about optimizing graphics and developer tools for Qualcomm's mobile hardware.